And of course, that's highlighting A, B, C, D, and E, those being the terminal nodes. We have the internal nodes, so these are inferred. Okay, the terminology here is inferred from these terminal nodes, and the internal nodes are these ones. Okay, good. Then we have.
Why is this one not
actually, probably this is just mislabeled, and this should have been there, and this here. Okay? I need to correct that one. So that should be there, and this here. Good eye. Okay? The branch length. So this is the evolutionary distance or the genetic distance, right? So the branch length. And if you look at A and B, we said that in that case, the genetic or the evolutionary distance is 0, which indicates phylogenetic identity. They are identical, they are similar. And then we have branch length, for example, between A and C is larger, indicating that their distance is related. Correct? And again, something that we went over, just highlighting the fact that the vertical distances are only for visual representation. They don't mean anything. Okay? All right. Now, we have the term that we use as called cluster. Okay? So remember, this is a general term that's used to refer to groups of samples. It's general. So A and B make up a cluster. Okay? D and E also make up a cluster. Right? But, I have this correctly, A, B, and C would also make a cluster. Again, it depends on the resolution of the data, how you want to look at it. Okay? So, the important thing to highlight here is this is a general term. It does not have any significance in terms of genetics, the word cluster. It's just a general term that is used to describe a group of sequences. Okay? All right. So what can you infer from a tree? So there are different things you can infer from a tree. For example, host switches. How a pathogen moves from one host to the next. Okay? We can understand spatial movements. How a pathogen moves from one location to another. Okay? We can look at transmission. Okay? From, let's say, one host to the next. Again, highlighting something like host switches. Okay? We can infer when a novel lineage emerged. So often, if your samples have dates, which they always should, you can tell when that novel lineage emerged. Is it last year? Is it last month? Okay? And also, of course, you can infer when novel mutations emerged. Okay? So we can infer very many things from a tree. As we finish, we have to think about common mistakes, common pitfalls that we make when we are building a tree. Not using enough background data. So tomorrow we'll see how we download background data. Okay? So let's say you are doing some sequencing for Mpox, correct? Nehemi has sequences from Burundi, right? What would you consider background data for your data set? clade 1b, you have clade 1b sequences from Burundi, right? And you want to add some background data set to your data set from Burundi. What would be the background data set you want to include?
For instance, we have some metadata, samples, regarding the patients, especially, they have to really include their skills.
Okay, we'll get to that. But what I mean is, you have clade 1b, okay? In addition to your own sequences, you, for example, you want, okay, I want clade 1b sequences from other countries. Let's say there is clade 1b in DRC. Let's say there's clade 1b in South Africa. And let's even assume, I know that's not the case now, let's assume we also have clade 1b from Germany and France. If you're thinking about background data set, which country's sequences would you think about first? Yes.
Yes.
Right? And even if you had to limit the number of sequences to include, for example, right? If you have sequences from North and South Kivu, you also have sequences from Kinshasa, right? First, you think about sequences from North and South Kivu, right? Because they are closer to Burundi than the Kinshasa ones, right? So, again, thinking about background data set is something we look at tomorrow, and even how to download and do an alignment to know those kinds of things. Is not using enough background data set is also something that can make your analysis not be successful. We talked about phylogenetic signal, like you're trying to establish evolutionary relationships, so you're looking at mutations. So your data set should have enough resolution, enough information to resolve the differences. Annotation errors. So you remember the example Stephen gave. So, you could have a sequence that has the wrong date. So somebody collected this sample in January, but sequence is in October. And then when they're submitting their sequence to GenBank, what date do they put? October. Is that correct? No. That's the sequencing date, not the collection. Because often you need to use the collection. Okay? Not removing recombinants. Remember we said you have to remove recombinants. Okay? Or at least mask them. Yeah? Or there could be like QC, not removing viruses with sequencing errors. So, you've done your assembly, but some areas have very low coverage. You allow them to continue, and then they have sequencing errors. So this can cause a problem to your phylogenetic analysis. And here, two last points. One, not questioning odd results. Like you have one sequence that has a very long branch. You're like, yay, I've discovered something new. You need to ask yourself, why is it a very long branch? Okay? You need to investigate. The last one is overinterpreting the gaps. Like you're saying, okay, this sequence is here, Germany. This sequence is here, DRC. Then you say like, well, I don't have a lot of information what happened between the samples in these two countries. And I'm just going to assume that, whatever is in my country in DRC came from Germany. So, like you're trying to overinterpret things that you don't know. Okay? So, we need to think about that as well. So, that is the end for today. So tomorrow, we continue with the practical. Okay. So, if you have Illumina and ONT, the first thing is there are different quality metrics for Illumina data and ONT. So you need to think about the quality cutoff for Illumina and ONT. So ONT, typically you're expecting to get between 10 and 20, right? So you might say, well, I'm going to use a cutoff of, I don't know, like 15. Again, but it has to depend on like what base calling mode did you use, okay? So you cannot say use the quality cutoffs for Illumina on ONT. The second thing is, we've talked about phylogenetic trees. So first you have to do an alignment. Different tools are made for different technologies, right? So there are aligners that are specific for aligners, pretty much it doesn't matter. So you'll have aligners that can align both ONT and Illumina assemblies, right? But for phylogenetics, I don't think it's much of a problem in the viral world as it is in the bacterial world. But in bacterial world, because they do have trees that are based on reads, it's going to be different like when we're using ONT reads. So I think if I think about what I would only be concerned about is the quality. So you have to be aware that obviously if you're using an assembly from Illumina, you expect it to be of higher quality than an assembly that has come from ONT. Yes.
Yeah, so we've done a couple of experiments to compare Illumina and ONT, right? I'm just trying to look at if we could get a difference in terms of the assemblies. The only regions where we got problems is where there was within host diversity and the allele frequency was slightly like ranging around 40, 30. So the different platforms could have, like your consensus could have a different, if it's A in ONT, it could be G in Illumina. Just that's because of the within host diversity. But where there is no much within host diversity, you don't get any. Like it's almost 100% similar.
Yeah, and actually there's some analysis we did for Vibrio, and we looked at data from Illumina versus ONT, and we were seeing a lot more variance, even for the super accuracy mode. So if you take super accuracy mode for ONT, and you take Illumina data, we were seeing more variance called on the ONT data than on the Illumina data.
Can we maybe discuss that in French as well?
Yeah.
So I was saying that, so he's asking the question, like, when you're looking at Illumina data, would you have the same expectations as when you're using ONT data? And I'm saying no. So I'm just,
It depends.
exactly. So I was saying that we've looked at some data that, you know, it was the same sample that we sequenced using super accuracy mode, which should be of high quality, and using Illumina data, which we know always is of high quality. And when you compare the two samples, we always see more variance called on the ONT than Illumina. Okay? And it's because, you know, obviously the ONT data is of lower quality, and you're going to get a few more variants that are called than you expect from Illumina data. But of course, at the end of the day, what you ask yourself is, if you got a tree that is built using Illumina data, and you built a tree that is based on ONT data, do you still get the same topology? Because at the end, it doesn't matter really if the topology is the same, right? If you're going to end up with the same conclusions, then the number of mutations don't matter. But if ONT is giving you a tree with a very different topology, then you need to be very worried. Okay? So there are people who actually, there are pipelines that can take hybrid assemblies. So you can use both ONT and Illumina, mix them together and, you know, call a tree based on hybrids.
Stan, before you translate, Arnold wants to share some experience where they've done a sort of direct head-to-head comparison. Can you maybe explain which pathogen you use for comparison?
Yeah. So this was for SARS-CoV-2. We picked a sample whereby we take the RNA, process it using an ONT workflow and the same sample in the Illumina workflow. So where you have a higher within host diversity or allele frequency that plays around, let's say 30-70. So you will find it's the inverse in ONT. So like let's say if on the Illumina data you had A, let's say at position 1000, A was 70% and G was 30%, you could get the inverse on ONT, right? But where you have very low within host diversity, then there is no difference in the consensus genome between ONT and Illumina, right? And that made us just use ONT moving forward.
Ce qu'il explique, c'est que généralement, lorsque vous voulez construire un arbre phylogénétique, vous allez, ce que vous allez chercher, c'est un génome consensus, n'est-ce pas? Et le génome consensus, comme on l'a expliqué depuis ce matin, il faut avoir des données de bonne qualité. Donc, quand on prend les Illumina et Oxford en Europe, par essence, Illumina produit des séquences de meilleure qualité de Oxford en Europe. Ça, c'est, si vous faites la ligne, vous allez regarder par défaut, Oxford en Europe produit de longues séquences avec une qualité de faible qualité, et Illumina produit des petites morceaux mais de grande qualité. Chaque technologie a ses avantages et ses inconvénients. Et quand vous allez construire votre génome consensus, si vous construisez un arbre phylogénétique et avec et que vous trouvez la même topologie, pas de problème. Donc, qu'est-ce qui va se passer si vous avez des topologies qui sont différentes? Donc, il faut avoir du recul sur ce que vous faites. Ce que les gens construisent généralement, lorsqu'on veut faire un assemblage, aujourd'hui on construit des approches hybrides où pour le même échantillon, on utilise, on fait un séquençage Oxford nanopore, un séquençage et on fait un assemblage hybride. Et ça nous permet, chaque technologie a ses avantages. Sur les Oxford nanopore, là où il y a des régions répétées, l'Oxford nanopore est beaucoup plus précis qu'Illumina. En termes de profondeur et de précision aussi, Illumina est beaucoup plus précis. Donc aujourd'hui, il y a des études pour lesquelles on fait un séquençage de tout, et c'est à partir du séquençage de tout qu'on construit.
So I'll also finalize with this quick example. So here,
ce qu'on est en train de faire ici, c'est pour des plateformes de comment faire ça que c'est.
C'est-à-dire que, je comprends, c'est-à-dire que la version de kit a été configurée sur vos machines, ça a été configuré pour les Illumina. Et vous avez des Oxford nanopore. Non. La phylogénie, ça n'a rien à voir.
I think there is, Stephen, have you used the ONT workflow on Epidemiology for Mpox? But it's there, right?
It's there.
So, yeah, just tell him that there's a separate workflow for ONT. Yes, that's available for Epidemiology. But anyway, last thing that I wanted to show was
Workflow for Shansu and platform.
I think idea it uses data from its processors.
so here we are looking at the number of. Remember, a tree is based on the number of variants that
It
you
is
call.
called take Mpox NF.
Okay, so here we looked at the number of variants that are called on Illumina data. You can see the number of variants here. Okay, of course, this is a log transformed for scale for the data, but on the y-axis, you have the actual number of variants. So here, what we are comparing was the base calling modes, and also for different versions of the Dorado tool.
Which pathogen?
So these were different pathogens. Okay, so that's why you see the distribution.
What kind of pathogens?
So these are bacterial pathogens. Okay, so we were looking at different pathogens and the number of variants that are called. Okay, so obviously, just looking at different base calling modes within ONT, you can see, for example, this ATCC strain for Vibrio, we have 3,000 variants if you use the first calling mode. If you use the high accuracy mode, this reduces to 68. And when you use the super accuracy mode, that reduces to 29. Again, you remember when we said speed versus accuracy? Yeah. So it's important to use the super accuracy mode if you can. Okay? Now, if you can. And now, because we are bioinformaticians, here what we are also trying to look at is model versions. So here we had version 420 and version 430. Okay? So let's see, this is super accuracy mode 420. You can see the number of variants that are called. This is version 430. You can see the quality improved. Okay? So also when you think about running tools, think about the software version that you're running. Is it a very old one? Is it a very recent one? Because sometimes the most recent ones have better accuracy than the old ones. Okay? So again, to answer your question, Illumina ONT, you are more likely, even if you think about phylogenetics, because it starts on a background that the data is lower quality, we expect that you're going to have, if you're just looking at the number of variants, there'll be a bit more. But at the end of the day, what I want to ask myself is the tree topology the same? If I have a tree for Illumina and a tree for ONT, do they look the same? Or is it different because of the different technology? If the topology is the same, whether you use Illumina or super accuracy mode, then it doesn't matter. Okay? But you see, this is something that you must test in your lab, for example, and see that, okay, you always get the same topology of the tree. Then it also gives you confidence that, moving forward, you can confidently use that technology to get some conclusions out of your data. Okay? All right. I think that's it for me.
Okay. Can we give the teaching assistants and the trainer one last round of applause? Thank you, James.